Hi Nidir. So we'll do carbonyl compounds now. Uh, okay, so we have covered till now, we have covered in organic chemistry, we have gone till alcohols, esters, and carboxylic acids, and that is what we discussed. Today we are going to discuss about carbonyl compounds, and it's going to be a little bit of a different chapter in the sense that it's going to be a little more advanced. We'll be talking about a few new things. I will cover right up till 18.6 hopefully in this video, and hopefully next time when we meet we can discuss infrared spectroscopy in person, because it has a few things that it is analysis of graphs and all, which we want to ideally be doing as an exercise together. These we'll be going through one step by step, so let's get started. Okay, so carbonyl compounds, right? So carbonyl compounds are simply only of two categories, which are anything that has the CO group, right? So this is the carbonyl group. This is what we call the carbonyl group. So we know that three groups have this, right? So one of them is R1 COR1, which is what we call a ketone, right? Then the next one will be this is called an aldehyde, of course, and the last one, take a guess, it is of course carboxylic acids. So we have talked about all of them actually in the last chapter a little bit. We talked about how alcohols can be oxidized to this. In particular, we talked about how primary alcohols go to this and the secondary alcohol go here, right? That is what we talked about last time. And then we also talked about how when these are oxidized further, let me try to draw that in a different color. So this is one layer of oxidation, and then this is the other layer of oxidation, right? And then we talked about, say, if we have to oxidize it further, then it just becomes CO2 plus water. This is what we talked about last time, correct? Okay, and what the other thing that we had talked about last time is the preparation of carboxylic acids through something we call the CN, which is called the nitrile group. And we said that we can hydrolyze it and get carboxylic acids, right? So this is just a preparation method using the nitrile group. So this is what we roughly talked about. We are going to pick up from here. We are going to see a few more things about testing. We are going to see a few more reactions, and mostly we'll be also having a section on this compound called HCN and how that will react with these compounds. Yeah. So let's get into it. Okay. So I've also highlighted some things in your book, so you can refer to it later. Okay. So first things first, let's start with the homologous series. As you know, homologous series is just any series. Let me try to write about it also. Homologous series, right? So we know that homologous series is nothing but that differs with CH2 in every iteration. So one homologous series that we have talked about is methane, ethane, propane, butane, and so on and so forth, right? And we know that all of them differ with this constant factor of CH2, right? So similarly, we want to discuss, so this was the homologous series of alkanes. Then similarly, you can have an homologous series of alkenes and alkynes and maybe even alcohols and everything. So we just want to discuss the homologous series here of uh, aldehydes and ketones, right? So the simplest aldehyde that we can have is HCHO, right? So the structure looks like this, of course. There's an H here and an H here. There's only one carbon atom right in the middle, and then both of them are H. Of course, it's called methanol. And then we can have CH3CHO. So now it will be H only on one side and then a CH3 on the other side, of course, right? So this becomes an ethanol. And then we can go on to have something like COCH3, right? Now this will be, we can either have this or we can have this, right? So there are two carbon atoms to the right here. If you see, these two are carbon atoms to the right, and then in this case there are one carbon atom to each side, right? So the problem is, if you're talking about the homologous series of aldehydes, in that case we would go from methanol, then go to ethanol, and then go to propanol, right? Because we're talking about aldehydes. But this, the other guy, is a ketone, right? So this is what we will call a propanone, right? So propanone is in some sense the first ketone that we can have. That's the easiest one. So the next one in this series would be something like this. Okay, so it will be called, uh, so let's try to name it. So it is butanone, butanone. Uh, but let's call it 2-butanone because it's on the second carbon atom, right? The group. And similarly here, it just simply carries on in the usual way. So for the aldehyde, it will just be butanol, right? So that's straightforward. Okay. So this is something that we understand fairly straightforward. So this is what your books also talks about. So the easiest one is propanone, then it goes to butanone, right? And the reason why they say butanone, we said 2-butanone. So let's come back to it. So because it can only be here, right? So if we try to draw the other uh, organic compound, then it would look like this, right? Like, which is the other numbering of this guy. I'm trying to draw a brother of this guy, 2-butanol. And this looks like it should be called 3. So one extra carbon atom here, my bad. So then this one and this one have the same, let me mark it, that we are talking about the same thing. So 1 and 2 here are basically the same compound and both are called 2-butanones. This is also 2-butanone and this is also 2-butanone. Because no isomers are possible, we can just call it butanone, right? Which is what your book does. So propanone and then comes to a butanone. You don't even need to mention the two. Okay, so this is what this, and then it says pentane 2-one and pentane 3-one, right? So we can see that this is a 1-3 carbon chain on the two sides, and in the other case it's a 2-2 carbon chain, which are these are structural isomers, right? So they have different names. Yeah. So this is basically in a nutshell about homologous series. Let's keep going. So we are going to now talk about preparation of aldehydes. Of course, one guess if you were to take about aldehyde preparation, what would it be? Of course, so one guess would be what we just talked about in the starting of this introduction of this chapter. We said that alcohols can be oxidized to give you aldehydes or ketones, only one of them. So how do you know which one you get? Is simply dependent on, as we said, the degree of the alcohol. If it's a first degree alcohol, so something like ROH, so like to be more particular, like CH2ROH, so it's a first degree alcohol, then this will definitely translate into ketone, into an aldehyde. If it's a R and then another RHOH, which is a second degree alcohol, then this will oxidize to a ketone, right? So this will oxidize to something like this guy, and then this guy would oxidize to something like, right? So which is an aldehyde group. Okay, now a natural conclusion is, hey, what happens to third degree alcohol? So the third degree alcohol will not form anything. So this reaction does not happen at all. So meaning that, say if you had R, C, R, R1, R2, R3, and then you have an OH here. So you see that we need to have a double bond here finally. So we can only have one and two additional bonds. But in this case, there are three bonds that are fixed. So we cannot upgrade this guy to a double bond O. So which is not possible. Hence a third degree alcohol reaction is not possible. Okay, so let's talk a little bit of specifics here about these two reactions that we talked about, like oxidation of alcohols. So the first thing that we need to know is what do we oxidize it by, right? So one of the first things that we talk about when we talk about oxidizing agents is acidified K2Cr2O7, right? So this is also used kind of like a test. So your book talks about this very nicely. So let's just read this paragraph a little bit. So it says the oxidizing agent used is a solution of potassium dichromate, right? Which is what we are talking about here, potassium dichromate. So potassium dichromate, like this is the potassium dichromate. So they say that it's orange and acidified with dilute sulfuric acid. Then they say that the primary alcohol is heated with this acidified dichromate solution and the reaction turns from orange to green. So you see that the chromium ions which are oxidized to a higher state themselves get reduced and they oxidize what they are oxidizing. So meaning that alcohol itself will get oxidized and K2Cr2O7 will get reduced itself. So when this gets reduced, it forms a Cr3 plus, and this is green in color. So this guy is green and the starting guy is orange. So we see a change from green to orange. So, so this is what they talk about here. Uh, so let's read about how this is done. So we can see that there is an ethanol, which is an alcohol, which is a first degree alcohol. It has an acidified, and you are adding a little bit of heat. So of course this is slowly change color. But one thing that they're doing is whatever aldehyde vapors will be formed here are taken out and condensed into a liquid again, which is ethanol, right? So the reason why you quickly keep removing the product is because if the aldehyde stays in the solution, then the aldehyde itself will be getting oxidized by the other potassium dichromate that's left and will be oxidized even further to carboxylic acids, which is of course something that we don't want. And so it's just all taken out and it is all distilled in. Of course, if this was a second degree alcohol, then this would not be an issue. And it can just form a ketone because ketones cannot get oxidized further to a carboxylic acid, right? So this is what they talk about here in this paragraph. Like ketone cannot be further oxidized, so it's not a big issue. So one more thing to notice here is this nascent oxygen, what we call, is written here. So this nascent oxygen is the symbol of an oxidizing agent, right? So if you don't want to mention K2Cr2O7 and all of that, you can just mention this oxygen. So just to be explicitly clear about all of this, I'll just mention it. So let me select a pen. So you can either write alcohol plus K2Cr2O7 acidified gives you, so in this case, let's try to write it exactly. So this for us, the exact thing that we are using is ethanol, and that is becoming ethanol, right? So this is one way to write it. Or the other way that you can write it is you can say that you want to form ethanol and you have ethanol and you are just using some oxidizing agent. Like so you just write like this. So this also means the same thing. It's just providing that extra oxidation, that extra oxygen that will oxidize this alcohol that is needed. So this is a symbol of an oxidizing agent, so to speak. You will see later when we talk about reducing agents, then this becomes a nascent hydrogen. Then this becomes a reducing agent, right? So, so we're trying to simplify things in chemistry sometimes by writing equation like this. Okay, so let's keep going. Okay. I would highly recommend to read through just these things. It is very straightforward and very easy. And once you get it, you will get it. Okay. So now that we have discussed preparation, the second thing that we always discuss is what can we do with it. So of course, the first thing that we can of course do is to reduce them back to alcohol, and that is pretty straightforward. So the two reagents that we use that we discussed last time also. So these are reducing agents that we use. So again, now we are going the other way. So if you have an aldehyde and you have a reducing agent, then this will give you a first degree alcohol, right? Now first of all we need to know, and again similarly for ketone, you get a second degree alcohol. I don't think there is an H after. I think it's like this. Yeah. Okay. So the example for a reducing agent, what we studied last time was sodium, aluminum, sorry, lithium. So let's look that up. Even I keep forgetting. So it's either, so, so let's look at the name together, right? It is lithium tetrahydrido aluminate. Okay, so let's look at this lithium and aluminate we see in the middle, and it says tetrahydrido. So lithium tetrahydrido aluminate, and the other thing that we use is, so let's take a guess at this name. It will be sodium tetrahydrido borate, right? Anyway, so the two things that we use are these guys, and then the other one is sodium tetrahydrido borate. Now, the one additional point that they mention is that the lithium guy is a stronger reducing agent, right? So one thing that they mention is they don't put it in water; they put it in what we call an ether solution. So which basically makes it a less reactive. So this is what they mention here. It must be dissolved in dry ether. And one example of an ether that they have used is diethyl ether. Uh, so they say that it needs to be dry because this is a more powerful reducing agent, right? But okay, at the end of the day, the idea is there is some reducing agent that's coming to from going from an aldehyde to an alcohol. So make sure you don't miss the forest because of the trees here. Just understand what is going on, and that is important. Okay. So, and then they proceed to give you an example, right? Feel free to like pause and just go through this example right here and see if it matches what it should with the balancing numbers and all. Okay, swiftly we keep moving. So yes, so the second reaction that we want to study with these things is an addition reaction. So something more precisely, it's the nucleophilic addition reaction with HCN, right? So this is one common reagent that we use to add, and we'll see what exactly happens. So let's get started. So there is a carbonyl uh, this thing, right? So it can either have an H here or an R here, and on the other side there will be an H or an R, right? It depends on whether it's an aldehyde or a ketone, but then it can be either, right? So in this guy, we add HCN, and what is formed finally is this guy. So this bond, this double bond O opens up, and then the H of HCN comes here, and the CN part of HCN comes here. Is that clear? How that's happening? Basically, this bond right here has opened up to give H on one side and the CN on the other side. So you can say that, okay, this is an addition reaction for sure. I understand that. Why is it called a nucleophilic addition? So the reason why it's a nucleophilic addition is we said, okay, so first things first, a nucleophile, uh, a nucleophile is something that has a negative charge, and an electrophile has a positive charge, right? So we say that a negative charge has been added, a negative charged compound has been added, but that does not seem to be the case because it looks like the Cn was the negative charge and H was the positive charge. We know that for sure. So it looks like both a negative charge also has been added and a positive charge also has been added. But when we define it like this, so we say that what was added first. So in this case, they are claiming to say that nucleophilic addition has happened. Basically, the nucleophile, which is the CN part of HCN, has reacted first. So the reason why they explain it in the textbook is they say that this bond, this C double O bond, because of the extremely different electronegativities between C and O, is very polarized. So this is already O negative and this is C positive. And then there is a tendency of this Cn minus, this cyanide ion, to come and attack this guy. So when it comes and attacks, it forms this intermediate where this negative charge is not satisfied yet, but this positive charge is fully satisfied by this incoming negative charge. And then this negative charge will be further satisfied by this H, and then it will form a stable compound. So in this way, we see that nucleophilic addition has happened. The negative charge has attacked first, and then of the positive charge came in later, right? So so this is why it's called the nucleophilic addition. So one thing that you need to understand is when after we always form two hydroxynitrile groups, right? So let's go back. Let's look at this guy. So what they're saying is if this is the first carbon atom, this is the second carbon atom, then we can say that on the two carbon atom there is a hydroxy group, which is the OH group, and then you have a nitrile at the end. right? So this is what they're saying. So this is of course not the complete name because we need to name these two parts as well. So but then you say that this group is present. We form a compound that is 2-hydroxynitrile, which has 2-hydroxynitrile in it. So they are saying that whenever HCN reacts, right, always 2-hydroxynitrile always forms. Okay, just a nomenclature thing this is. The other thing that you need to understand is if you look at this, if say, let's take an example, okay? So if say we had a aldehyde and we had an R here and you added HCN, so the C double bond O, so no double bond O, it will form an OH here and then a C and then a triple bond N and then H here, right? So we see that if we compare the original reactant to the final product, it looks like one carbon has been, our original carbon chain was this long, and now our carbon chain is 3 carbons long, right? So it looks like we have added a carbon to our carbon chain. So this is very important because this way we can increase the length. So if you start with an ethanol, we can get a propanol and then so on and so forth. Which is why this HCN compound is important because it helps us increase the length of our carbon chains. Okay. So your book also talks about these ideas, which is nice. Okay. So the last topic that, so the second last topic that we'll talk about is this testing idea. So let's go through it in your book only. Uh, okay. So let me just give you a short introduction about what we are going to talk about. So we're going to talk about testing of aldehydes and ketones. So what are we testing? We are testing whether, so we are done with the reactions part. Now we are going into testing. So we are going to test whether these functional groups are present in the organic compound or not. So you are just given a liquid which is transparent maybe. You want to test whether it has a CHO group or whether it has a CO R1 R2 group, right? We want to check whether it has a carbonyl group or not. So it's a test for a carbonyl group basically, right? So one of the easiest ways that you can think about this is uh, so first of all, you want to test for a carbonyl group and then you want to test whether it's an aldehyde or a ketone. So they will talk about 3 tests which we are going to go through one by one and let's see what they do, right? So the first test is what we're going to talk about is for a carbonyl group. The second test, which will be with something called DNPH, 2,4-DNPH, we'll talk about what that is. That will tell us whether this test will tell us whether there is a carbonyl group or not. In the second thing, we'll talk about how to differentiate between aldehydes and ketones using 2 reagents. One will be called Tollens reagent, and another one will be called. Let's see, even I have forgotten. So the other one will be called Fehling solution, and we'll go through them one by one. So just to start you off on DNPH, so the full form of DNPH, 2,4-DNPH, is 2,4 dinitro phenyl hydrazine. So let's try to break them down one by one. So hydrazine, I don't know if you have seen this before, but hydrazine is NH2, single bond NH2. So you can see that it was NH3, but then one H is removed and then two NH3s, NH2, NH2 are connected with each other, right? So this is hydrazine. It is generally a very unstable, very highly reactive compound. Now what is phenylhydrazine? So phenyl is nothing but a benzene ring and that you attach to one NH and then an NH2. So this will be a phenyl hydrazine, and after this you say it was 2,4 dinitro. So you want to attach a nitro here, and you want to attach a nitro right here. So this is the structure of 2,4-dinitrohydrazine. So this is exactly what they talk about here. This is the compound that they start with, right? Okay. So just so, but then most likely it is just a solvent for you. It's an organic solvent. It will be called 2,4-DNPH, and that is all you need to remember. So the what happens with 2,4-DNPH is we have a condensation reaction, meaning that H2O comes out, right? So if you see that there is an H2 from here and O from the carbonyl, that will be condensed, and then you will form this C double bond N right here. This C double bond O will be replaced by this thing, right? And this is kind of like a heavier salt, and this kind makes a precipitate, right? So so they're saying it's a very easy test for a carbonyl group. So let's look at how what they're doing. So they're just saying that adding a solution of 2,4-DNPH, if an aldehyde or ketone is present, a deep orange precipitate is formed, and the precipitate formed is that of this guy, this hydrazone, right? So, and just to again take a step back and understanding, this will form a precipitate with both aldehyde and ketone. We don't know yet whether it's an aldehyde or ketone. We just know that the C double bond O group is present, right? So in this example, they have used an aldehyde, but it could well be a ketone also. Okay, it would still form this orange precipitate. So the next question is, how do you differentiate between an aldehyde and a ketone? Is to have one more step where we know that we do an oxidizing step. So if we oxidize an aldehyde to an acid, that is possible, but a ketone to an acid is not possible, right? So what we can then do is we can test for that COOH group. So let's go into this in a little bit more detail, right? So first an oxidizing step, and then try to do something with that acid that's formed. So the first reaction is first reagent, that is Tolen's test or Tolen's reagent. So this Tolen is basically a silver nitrate solution with excess ammonia. Okay. So first we need to do oxidation. So who will do the oxidation is the silver plus ions that we have, right? So the silver itself is a very stable thing. It exists in nature, right? The silver thing. So it is happy to be converted back into solid silver, an elemental, a pure silver. So we see that here there are ions. So they want themselves to get reduced into pure silver. So they will themselves oxidize something else. So they act as a mild oxidizing agent. And that is perfect for us because that mild oxidizing agent can work with the aldehyde, and it can oxidize the aldehyde to an acid. So that's step one done. Okay. And then what we do is, because there are further alkaline conditions, because you have an acid that's formed, so alkaline plus acid makes a salt and a water, which is the silver salt. And on top of this, so from a standby point of view, you originally start with a clear solution, you add silver solution, and then you add a ammonium solution, which makes it basic. Then what you see is the silver gets oxidized, silver gets reduced itself and makes a pure silver, which forms this coating, and the solution itself becomes acidic, which reacts with the basic nature of the solution to form a salt inside this and water. So whenever you see this reaction will only happen with aldehydes, because only aldehydes can go to acid. Okay. Okay. And the last thing is a failing solution. Okay. And what that contains is copper 2 plus ions. So the only difference here is the copper 2 plus ions themselves get reduced to copper 1 plus ions, which again oxidizes the aldehyde to an acid. And here what we see, is a color change. Copper 2 plus is blue in color and copper 1 plus is red in color. So as soon as you see a color change, you're like, yes, this is an aldehyde. So again, taking a step back, you first want to test for an carbonyl group. So first you want to do this test with 2,4-DNPH and you want to see this precipitate. And then you want to test for whether any single test that you can do, whether with Tollens or with Fellings. And you can just see whether you see a change in color, then you're like, yes, this will be an aldehyde if the color changes. If nothing happens, as will be the case with ketones, then you are good. There is no issue. Awesome. Okay. Okay. And the last thing that we talk about here is okay, you know what? Let's do it this time. Next time. This 18.6 and 18.7, let's cover next time when we meet. Okay. Okay. See you.